Hey guys, how's it going? So in the last tutorial on BURAI, which is a GUI of Quantum Espresso, we covered a lot of stuff like performing geometrical manipulations like creating a vacancy or introducing an impurity or even creating a supercell or a super slab using the modeling feature of this program. So in this tutorial, what we'll be doing is we'll be covering how to perform an SCF calculation. So this is the first tutorial in which we'll be performing any particular kind of calculation. So in order to perform an SCF calculation, we need some systems. So for this tutorial, what I'll do is we'll be using a silicon crystal lattice. So head over to the My Projects tab in the BURAI home folder or home tab, and then head over to the examples, and then you can open the SCF folder and then select either of these silicon SCF files. So just go ahead and open one of these. So now in the geometry tab of this software, what you can see is you can see all the geometrical aspects of this system, like it has cubic Bravell lattice, and then we have the lattice parameter, and then we have the positions of the atoms, and then we can choose the pseudo potential. In this particular tutorial, we will be using the ultra soft pseudo potential, that is this one. So it has nonlinear core correction, that is, you can see it right here. So NL also denotes that, then PB denotes that it is a GGA kind of exchange correlational functional, and then RRKJUS. So here US means the ultra soft pseudo potential, right? So we'll be using this particular pseudo potential, and we already know that the suggested cutoff for wave function is 43 Rydbergs for this particular pseudo potential. So just go ahead and double click on it to select it. Now everything in the geometry tabs looks alright, so just go ahead and click on the SCF tab to perform an SCF calculation. Now here are a number of settings that you might wanna customize or change according to your needs. So we'll be going one by one through all of these. So first of all, we have the restart mode. So this one is used in case if you don't want to start your calculations from scratch and you have already performed some calculations, then you can have the restart mode as yes, so that it picks up the temporary files that were, or the all other kinds of files that were created in the previous run. So it will use that instead of calculating everything from scratch. So if you have it on yes mode, then what you will notice in the input file is that you will see that the restart mode parameter of the Quantum Espresso is set to restart. However, if you change it to no and reload the input file, then you will see that the restart mode is basically from scratch. So the default value, even if you don't provide this parameter, then it is from scratch. So since this is the first calculation, so restart mode set to yes doesn't make any sense, so we'll just keep it on scratch. And it is also useful, like sometimes if you're performing lengthy calculations, then if you properly terminate your calculations, then you can later on start or resume the calculations by setting the restart mode to yes. Then we have the maximum time. So this sets the it is pretty much self-explanatory that it sets the maximum time that your calculation is going to run or is going to be allowed to run. So for now it is set to 24 hours in so you can see this number, this corresponds to 24 hours I guess in seconds. However, you can change it to whatever you want. So that's that. And then you have two options, that is whether you want to calculate the force and stress or not. So if you set these to yes, then you will notice that the input file would have these two more parameters. That is the Quantum Espresso software will now be calculating the force as well as the stress. However, if you set it to no, then these two will become false, and the default value is again false. Then we have another important part, that is the plane waves. So here what we have is we can set the cutoff for the wave function as well as the charge density. So as we already know, that we saw from the pseudo potential file here, that the suggested cutoff for the wave function was 43 Rydbergs. So we should probably change that in our case to 43 Rydbergs. However, there is a method to calculate or find out whatever your whatever is the optimum cutoff for the wave function. So that method is called the method of convergence, I guess. So what you do is you calculate the energies at different cutoff energies, that is like at 10 Rydberg, 15 Rydberg, 20 Rydberg, and so on. So you keep on doing that, and then you see how the energy is changing. So if the energy is not changing by much, then you can find out the cutoff wave function in that process. However, now coming to the cutoff for charge, now by default the quantum espresso takes the charge cutoff as basically 4 times that of the cutoff for the wave function for a normal potential. Now since we are using an ultra soft potential, it is suggested that in case of ultra soft pseudo potentials, what we need is the cutoff charge as about 8 to 12 times the cutoff for wave functions. So let's go ahead and set it to like 10 times, so 430 Rydberg. So just hit enter, and then you can see that the the input file would now have these changes. So the cutoff for the wave function is 43 Rydbergs, while the cutoff for the charge density is basically 430 Rydbergs. So you can set these parameters. Then we have the K point grid here. So again there is a method to find out the optimum K point grid, and that is again the method of convergence. That is, you find out the energies at, or basically what you do is you run an SCF calculation at different number of K points, like we will run them for 8 or 222 or 444 number, and then we will notice that for what number the energy starts changing by much, and then we will call that our optimum or convergent K point grid. So for this tutorial, let's just assume and okay, now let me just use a 4x4x4 grid, because this would be pretty small and faster to calculate. So for this tutorial we'll be using a 4x4x4 grid. However, you can increase it to whatever you want. Then coming to the occupations part, now here we have two options, that is smearing and fixed. Now Quantum Espresso recommends that for semiconductors or insulators we use the fixed part if we want to get the the band gap in the SCF calculation. However, for metals you can just use smearing here, and then if you are using occupations as smearing, then you have to provide what kind of smearing. Then you can choose any of these, whichever you prefer, and then you can set the smearing width as well in different units. And then you will see all these changes being reflected in the input file, like the occupation, smearing, and all that stuff. Now for this tutorial, let me just go ahead and change it to fixed, so that we calculate the so that since we are calculating this for an insulator or a semiconductor, and then what we are also going to do is we are going to add one more parameter, that is called NBND, that is number of bands, and we will set that to okay, so to find out the value, let me just go here, and we will see that the number of bands should be 32. So let me just go ahead and add that parameter, and band equal to 32, and click here so that it saves that. Now what this is going to do is it will help me to find out the band gap. So if we have the occupations as fixed, then Quantum Espresso will return the energy of the highest occupied level. Now if I provide more number of bands, then what it will do is it will calculate the energies of electrons in the conduction band as well, and then it will provide me two energies, that is the highest occupied level and the lowest unoccupied level. So, and that way if we provide a high number of bands, you will be able to get the band gap from the SCF calculation itself. So that is why we are doing that. And then coming back to the settings in the SCF tab, so we have covered all these standard settings. Then coming to the electronic optimization, now here what you have is you have the option to set the maximum number of steps. So when an SCF calculation is run, basically what it does is it performs various number of iterations. So here you can set that what is the maximum number of iterations that you want in case your calculations are not converging. So default value is 100, but here we have set it to 201. So I mean the Quantum Espresso default is 100, however the BURAI default is 200, as you can see right here. So you can change that accordingly. However, usually systems usually converge with around like 10 to 30 iterations at max. And then we have the threshold for the convergence. So basically the quantum espresso software calculates the energy at each iteration, and the threshold value tells you, or the quantum espresso, that when to stop the iterations. That is, if the energies are not changing by more than 10 to the power minus 6 Rydbergs, then it will consider the calculation as converged. So you can change that according to your needs. Currently it is set to 10 to the power minus 6 Rydbergs, which is pretty good enough. And then we have the wave function option. So here you can set whether you want to have the initial guess as purely atomic, or you want it to be atomic plus random. And then there is a random option, and then you have a file option, so you can provide a file containing this information. So let's just stick to the default atomic plus random, and then you have the option to choose the diagonalization algorithm that will be implemented. So here are the three choices, but we'll just stick to the default. And then we have the option to set the charge density, whether you want it to be atomic or file. So we'll just stick to the default atomic value. And in case you are setting it to file, then you will need to provide the address to the temporary directory which is storing all this stuff. So when quantum espresso performs a calculation, it stores a bunch of stuff in a temporary directory. So if you set it to file, then you will need to give it the information about that file, that is where it is stored, and that would be given using the an option called out directory. And don't worry about it, I'll probably cover that in a future tutorial, but for this tutorial we'll just stick to atomic. And then we have the mixing method, and then we have the the mixing beta value, that is how much mixing you want to be done. So basically what it is that after each SCF calculation, it just uses some part of that electron density and some part of the new electron density. And so using this mixing beta option, which is currently set to 0.7, you provide the information like how much mixing of the new and old electron densities you want to be there and all that stuff. And by the way, starting WFC is set to atomic plus random from here, and then the starting potential is set to atomic from here. So you can see any changes you make here in this ampersand electrons name list. So this is the electrons name list, and any change you make in this electronic optimization setting, then they will show up here. And then coming to the magnetization and GGA plus U. Now sometimes what you have is you have a magnetic system like Fe or nickel or any other like that. Then you have the option to perform spin polarized calculations. So to perform spin polarized calculations, just set it to collinear, and then when you reload this, then you will notice an option called n spin is equal to 2 appear. So n spin equal to 1 basically means non-spin polarized calculations, and 2 for spin polarized calculations. And then you have the what you need to do is you need to provide the number of electrons in the upspin configuration, or the number of electrons in the downspin configuration. Now let's say if we were performing this calculation for iron, then what we'll do is we'll probably have all the electrons in the upspin configuration. So if you want all the electrons to be in the upspin configuration, then you give it 1, and if you want all the electrons to be in the downspin configuration, then you give the parameter -1. And anything like in decimals basically just means if it is positive, it means that 50% of the electrons are in the upspin configuration, and if you give -0.5, then it means like 50% of the electrons have downspins. So that is how you use the spin polarized calculations to evaluate the things like magnetic moments, or maybe density of states which are spin polarized and all that. And then you have another thing called the fixing of magnetization. So sometimes what you want to do is you want to provide an external magnetic field. So in order to simulate that, what you can do is you can provide a total magnetic field, and you can give the value in the Bohr magneton along the z-axis here. And if you perform non-collinear calculations, then you can fix the magnetic field in all the 3 directions, and you can even provide the starting magnetizations in all the 3 directions. Now coming back to the collinear magnetization, so any changes you make here, they come into the category of starting magnetization. So that is the quantum espresso input parameter. and you can find out more about that in the input file help of the Quantum Espresso. So that's all. However, since silicon is obviously non-magnetic, so let's just stick to non-polarized calculations. However, even if you are performing spin polarized calculations using the collinear tab, and even if you provide some starting magnetization, you don't need to worry, because the system will automatically, after all these iterations, it will all automatically be in a non-magnetized state. So that's how you will know if your system is modeled or is predicted to be magnetized or non-magnetized using DFT. So that's all in the magnetization tab. Now coming to the GGA plus U. So typically what it was seen was that the conventional DFT methods like GGA were underestimating the band gaps, and that was because the DFT was over delocalizing the electronic orbitals, or the electronic states, I guess. So conventional GGA over delocalizes these states. However, there is a setting called the Hubbard correction. So you can use Hubbard correction to what it does is basically it localizes the the electronic states, and what it does is it brings the valence band states a little further apart from the conduction band, and hence increasing the band gap. So it solves the problem of underestimation for most of the systems. However, it's still not perfect. And so basically, to implement such a Hubbard correction, what you do is you select yes, and then you will notice that there will be a parameter called LDA plus U set to true. So basically now you are performing a DFT plus U calculation, and then you can set the Hubbard parameter as whatever you want. So you can set it to like 5 electron volts or something like that. However, for this particular tutorial, we'll just be sticking to conventional DFT calculation. So that's all the settings in the SCF tab of the BURAI software. And then I already covered the K points. That is the it basically specifies the Monk-Hart-Pack grid. I'm not sure how to pronounce that, but so Monk-Hart-Pack grid or something like that. So it basically gives the size of that. So currently we are using a 4x4x4 K point grid, and these three numbers basically tell the offset of these grids. So basically how the grid is displayed. So currently we are using a 0 offset. However, you can change that according to your needs. And K point automatic basically means, and this particular setting automatic basically means that we are using a Monk-Hart-Pack grid. However, if you are using or calculating only a you are performing only a gamma point calculation, then you can set it to gamma as well. So you'll just change it to gamma, and then I don't think you'll be needing to provide these. However, if you are changing it to crystal B or 2 pi by A kind of things, then you can even provide the K point path, like along which symmetry points you want this calculation to run. However, it is a good idea to just perform an automatic kind of calculation for the SCF, and then give a high symmetry path for the band structure calculations. But for SCF and density of states, I usually provide a Monk-Hart-Pack grid. And then we have all these geometrical properties that we already covered in the last tutorial. So we have probably covered all these stuff that is here. So I guess now we are ready to run our calculation. So just go ahead and click on here and then select run. Now it will prompt you to save your project. So just go ahead and do that first. So silicon SCF test. Alright, then hit enter. And then what it will tell you is, it will ask you that how many processes you want this to be running on, and then how many threads you want it to be running. So I have set both of these to 4. However, just increasing this number doesn't mean that your calculation will scale infinitely faster. It depends on the configuration of your PC, that is how many cores and threads your processor has. So, and then you have the host name, which is just localhost currently, and then you have the job type. So we are running the SCF calculation for now, so it is set to SCF, and then just go ahead and hit enter or OK. And then coming back to our SCF test, then if you click here and click on result, then you will notice that there will be 2 files. So in basically tells you how the input file looks, and the log.scf basically shows you the the output file of the SCF calculation. So as you can see that it tells you that program PWSCF was started on 1st Jan at this time and all that stuff, and how many processes was it launched on. Like it was launched on 16 processors, like 4 processors and 4 threads per process, so that makes it 16. And then here you have the first iteration going on, so it tells you that curve is set to this and we have this mixing beta value, and it is currently performing the Davidson diagonalization. Now if you reload it, then you can see that how many more iterations have been performed since then, and you can see that currently we are on 5th iteration. Now coming back, and you'll notice that there's another file called scf.in. so it is a cool little graphical plot that shows you how the SCF or the total energies are converging in this SCF calculation. So as you can see that after 5 iterations we have the SCF has converged. So coming back to the output file, now here you can notice that since we set the force and stress calculation to true, so we will have those things calculated here. Or okay, I think that we turn them off. Okay, so we turn the force and stress calculations off, by the way. However, if they were true, then we would have them being shown in the last. However, currently you have the total energy and all the contributions to that from here, and then the important thing is the highest occupied and the lowest unoccupied level. So this will give you the band gap. Now currently you can see that it is something around 0.69 or something, so which is a pretty underestimation of the silicon band gap, which is known to be like 1.1 electron volts. So that is how you perform an SCF calculation, and that's it, I guess. So at each iteration you can see that how is the energy changing. So at the first iteration we had the energy to be minus 81.746. Then at the second iteration it was minus 81.755. So there was a change of like 0.008 in these two energies. Then in the fourth iteration we had the energy as minus 81.7557. So you can see that at this step we had an estimated SCF accuracy of less than 0.000000106. so that's like 5 decimal places. And then finally after 5 iterations we achieved our SCF accuracy or convergence threshold, that is 10 to the power minus 6. So that's it. Sorry for this video being too long. Hope you guys enjoyed it and learned something from it, and in case you did, then don't forget to hit the like button and subscribe to my channel for more videos like this. Thanks for watching and have a great day.